Now let's take a look at how we represent these orbitals in space. We've already seen, from a simple standpoint, over on the left-hand side of the page here, we have a 1s orbital, 2s orbital, 3s orbital, showing that those orbitals, or those regions in space where we feel the electron density gets larger and larger as the orbital, as the energy level gets higher and higher, it gets farther away from the nucleus. If we take a closer look at this, the graphs on the right depict the probability of finding the electron as a function of the distance from the radius. Now, it's hard to kind of describe this, and we'll see in just a minute, what this looks like in 3 dimensions. But if we look at the 1s orbital here, we see that at a certain distance, there's a maximum probability of finding the electron, and then it falls off and goes out as you get farther away from the nucleus. Something interesting happens when we look at the 2s orbital. There's actually 2 peaks, right? One that occurs around half an angstrom, and then the other one that occurs around 3 angstroms in distance away from the nucleus, where there's 2 peaks in the electron density, and then more significantly, around 1 angstrom, there's what's called a node. And a node is a place where there is 0 electron density. What this means is that if you went out from the nucleus in any direction at a distance of about 1 angstrom, and this is for a hydrogen atom, at a distance of about 1 angstrom, there would be 0 electron density. There would be 0 feel for an electron, due to the electrons that were in the 2s orbital. Right? And we see the same thing when we get to the 3s orbital. We have maximum at 3 different points where the electron density reaches a peak, but we also have these 2 nodes that occur where there would be no electron density. And you notice in the third the 3s, up at the third energy level, most of the electron density is out farther away from the nucleus, which is what we would expect. It has more energy, so most of the electron density is going to be out farther away from the nucleus. However, this little bit of energy that is closer to the nucleus, or this little bit of electron density closer to the nucleus, will come into play in some of the properties of the elements. So we'll see that later on. Here we have a cutaway view of the cloud model of the atom, the orbital, the s orbitals, which might give you a better, kind of 3-dimensional picture of what's going on. So you can see that in the first one, on the left, the electron density is distributed, from the center of the atom out to where it goes down. But here in the 2s, right, you have a maximum density, and then there's that node, that colorless region in between the dark region toward the nucleus and then the darker region toward the outside. That white ring around there that's a sphere in shape would represent a node, again, where there's no electron density. And then in the third one, you would see the 2 nodes. Again, these are at radial distances away from the nucleus, so they would be basically a sphere in shape around the nucleus. So if we go beyond just looking at the s's, we have our shape for our p orbitals. Again, over here on the left, we have a kind of a cloud image of this, where it's more of a fuzzy, blurred region. And then to try and understand the directionality of these things, we create more hard surfaces. So the ones on the right represent the orbitals in more of a solid depiction, where we have the pz, the px, and the py. So again, those 3 orbitals that are oriented in different directions in space, which we didn't talk about as much the first time go around with this, but those will come into play much more as we discuss things this year in AP Chemistry. Continuing on up, we have our d orbitals. And for the d orbitals, we have additional regions of space. So the s was a single sphere, the p's were a dumbbell shaped, the d's we have 4 lobes on the dumbbells. And one of the things we're going to have to come to grips with is, even though there are 4 lobes, we can still only put 2 electrons in each d orbital. So how do we get the feeling of electron density in all 4 lobes, even though we have 2 electrons? Well, we have to remember that the electron has wave properties to it. And one of the properties of waves, is that you can feel the presence of the electron all over the place. Right? So the wave properties, the characteristics of the wave can be felt in all 4 lobes without the particle part to it actually being in that lobe. So there are d orbitals, and then if we go a little bit further onto our f orbitals, we end up with even more lobes on these. So you can see their depiction up here. And so we won't be doing too much with the f orbitals, but they're just kind of interesting to see what those lobes look like. So next up, we'll work on what happens when we deal with atoms that have more than 1 electron, and then how does that factor into things.